Hi, and welcome to Dr. V's Chemistry Webcast. The focus for today, pH calculations. Chemistry students need to be able to calculate pH, and we have several new equations that are very important that we're going to introduce. You'll definitely want to keep a calculator handy. So I need to start by stepping back a little bit and revisiting logarithms. I don't know if you've seen logarithms in your math classes to date or not, but if you haven't, let's just do a really quick overview. We're working with the base 10 log or the common log. And here's how this function works. If you're taking the log of 10 raised to some power x, the log of 10 to the x is x. And that's the pattern that we're working with, right? So 10 to the 0, of course, would be 1, all right? So the log of 1 is 0. The log of 10 raised to the power of 1 is 1. The log of 100, 10 squared, is 2. The log of 1,000, or 10 cubed, is 3. So we're changing our values from 1 to 1,000, and yet when we take the log of it, it only ranges from 0 to 3. Really taking big changes and making the scale much more manageable. Logarithmic scales end up being really important because they do take these very large changes and linearize them. So the Richter scale is a logarithmic scale, right? A 5 magnitude earthquake is 10 times stronger than a magnitude 4 earthquake. The decibel scale is also a logarithmic scale. The stellar magnitude scale also uses logarithms. I couldn't find any really pretty visuals of that, so I didn't include that here. And the pH scale is also logarithmic and becomes very important there. All right, so the definition of a pH, this was established by Søren Sørensen, the Danish chemist, in 1907. He defined the pH as the negative log of the hydronium ion concentration, or the negative log of the hydrogen ion concentration. We can use hydronium ion and hydrogen ion interchangeably here. All right, so what this means is that as the hydrogen ion concentration increases, the pH of the solution goes down. The more acidic your solution, the lower the pH, all right? So the other thing to keep in mind is that we're using the square brackets around the hydronium ion and around the hydrogen ion because we're saying that we're talking about molarity here, molar concentration, moles of H3O plus in a liter of solution. When we think about the pH scale, all right, there's a lot going on here. We know acidic solutions have low pH. Basic solutions have pH greater than 7, okay? But we can also think about it on a particle level. To be an acidic solution, we're saying that there are more hydrogen ions in solution than hydroxide ions, right? And a basic solution has more hydroxide ions than hydrogen ions. A neutral solution has those two concentrations being equal. But let's get back to the logarithmic nature of the scale. All right, if I have a 10-fold change in the hydrogen ion concentration, I'm going to have a 1 pH unit change. All right, so order of magnitude in concentration is only a 1 pH unit change. So a solution that has a pH of 5 has 10 times more hydrogen ion concentrations than a solution with a pH of 6. All right, so big changes, and yet the pH doesn't change by that much on that logarithmic scale. Very interesting. So we go back to our pH definition. The pH is the negative log of the hydronium ion concentration. Now we want to be able to do this in the other direction. If I have a pH, I want to be able to calculate the hydronium ion concentration. So I do that with 10 to the negative pH. If you haven't written down these equations yet, then this is the time to do that, okay? Go ahead and just write those down. You're going to find you use these equations a lot. Keep them handy. I even recommend memorizing them. So just as a reminder, those square brackets mean I'm dealing with molar concentrations here. Okay, let's do some really simple pH calculations. Now, if you know your logarithm rules, you may find you can do these without a calculator. That's actually very achievable. And once you see the pattern here, you're going to pick that up very quickly. So let's say the hydrogen ion concentration is 10 to the minus third molar, and I want to know the pH. Well, I need to take the negative log of 10 to the minus third. The pH is 3. Oh, see, the exponent gives me the pH. This would be an acidic solution. What if the hydrogen ion concentration is 10 to the minus 9th molar? This is a much smaller number, all right? Well, I take the negative log of 10 to the minus 9th, I get 9, pH of 9. That's a basic solution. Let's do some more problems. All right, if the pH is 11, let's get to the hydrogen ion concentration. All right, so I have to do 10 to the negative 11 All right, and that's my hydrogen ion concentration. This is also a basic solution. If the hydrogen ion concentration is 10 to the minus 7th, what's the pH? The pH would be 7, and we'd say that's a neutral solution. What if the pH is 2? What's the hydronium ion concentration? It would be 10 to the minus 2 molar, and that would be an acidic solution. So if you're writing it in scientific notation, right, the exponent basically gives you the pH. I shouldn't say basically there, maybe, but you see the pattern. Okay. Now, they're not always going to be this simple because it's not always, the coefficient for the scientific notation isn't always 1. So we will have to do some practice with those as well. Before I go and do those practice problems, I wanted to introduce another term called POH. All right. As you might imagine, this involves the hydroxide ion. All right. The POH is defined as the negative log of the hydroxide ion concentration. So it's very similar to the pH formula. We can also go in the reverse direction. If I have the POH and I want to calculate the hydroxide ion concentration, I do 10 to the negative POH. Write these equations down. You're going to need them. Like now, go ahead and write them down. And it's time to get out your calculator because we have some calculations to do. So let's do problem number 1. What is the pH of a solution if the hydronium ion concentration is 0.45 molar? So I gave you the hydronium ion concentration as 0.45 molar. Notice that there are 2 significant figures in this molarity. That's going to be important later. So I need to use the pH formula, the negative log of the H3O plus concentration, which was given to me. So I can substitute that in to my formula. And I get a pH of 0.35. Okay, so there are a couple of things going on here. One is that you need to know how your calculator requires you to enter these different numbers. All right, so depending on the calculator you're doing, it will be a little bit different. So on my little Casio calculator, I would do 0.45 and then hit the log button and then multiply by -1. If you're using the TI-84s and those graphing calculators, you would do the negative log. You'd hit negative log button and then 0.45 and close your parentheses, and you should get the answer. You need to pause this and play with your calculator and make sure that you can put these in and get to the correct answer with your calculator so you know all its little quirks. Okay. The other thing I wanted to point out was the sig fig rule. Because the pH scale is logarithmic, we end up reporting the sig figs a little bit differently than what we had done earlier in the course. All right. There are 2 sig figs in the molarity, as I had mentioned earlier. So in the logarithmic scale for the pH, only digits after the decimal are considered to be significant. So I need 2 digits after the decimal place for this pH, 0.35. It's a very low pH. This is a pretty acidic solution. Okay, we're going to see this again and again. It's called the Mantissa rule, but what's really important is not that you know the rule by name, but that you know how to apply it for your pH calculations. Okay, let's go on and do another problem. The pH of a cup of coffee was measured and found to be 5.5. What is the hydronium ion concentration? All right, so we're given a pH. Notice there's only 1 digit after the decimal. All right, so there's only 1 sig fig in that pH measurement. To find the hydronium ion concentration, it's 10 to the negative pH. So I can substitute in 10 to the negative 5.5, and I need to put that into my calculator to get the answer. Okay, so this again, you need to pay attention to how your calculator does the entry. All right, when I get my final answer, since there was only 1 digit after the decimal in that pH, I can only report 1 sig fig in my H3O plus molarity. Okay, so it's 3 times 10 to the minus 6. That's reasonable. The pH was 5.5, having an exponent of 6. That's close. I can sort of estimate and predict and make sure my answer makes sense. But again, you have to pay attention to entry order for your calculator. All right. So again, on my calculator, I have to, my little Casio, which is not a graphing calculator, I have to do negative 5.5, and then I do the 10th and X button on my calculator. On the graphing calculator, it's on the TI-84s, you would do the 10 to the X button and then the negative 5.5. You have to make sure that negative number is in there, or it will give you really weird answers or give you an error. And make sure you know how to enter this into your calculator so that you get the correct answer. All right. All right, let's go on to problem number 3. Calculate the pOH of a solution if the hydroxide ion concentration is 1.45 times 10 to the minus 8th molar. Okay, great. So I've already highlighted that. Notice there are 3 sig figs in the molarity as written. Okay, so The pOH is defined as the negative log of the hydroxide ion concentration, which I was given. Let's substitute that in. All right. And again, we need to put that into our calculator. We know there are 3 sig figs. So I'm going to report my pOH with 3 digits after the decimal. All right. Again, pay attention to your calculator that you're putting it in, that you can use your calculator to get this correct answer. Okay. In order to go on and do more involved problems, I need to revisit the idea of water being an amphiprotic substance that can autoionize. Water can act as both an acid and a base and give away H pluses and accept H pluses. When that happens, you form hydronium ion and hydroxide ion in solution. Okay, and we can write an equilibrium constant expression for this. We call it Kw. Not so surprising that it's Kw for water, right? The liquid waters on the reactant side we don't include, so we're just really talking about the ions. Right, so the hydronium ion concentration times the hydroxide ion concentration, this equilibrium constant is often referred to as Kw. And it has been measured in water, and it's a very, very small number. Right, 1 times 10 to the minus 14th. In fact, I want you to write this expression down. Kw equals H3O plus times OH minus equals 1 times 10 to the minus 14th. It's a really handy expression. Right. This equilibrium very much favors reactants. Only tiny, tiny amounts of hydronium ion and hydroxide ion are present in pure water. But it does have an equilibrium constant that's not 0. Okay, so write that down. That's really handy. Now there's another piece to this, all right? If we look at the pH and the pOH, we can actually see that the pH plus the pOH add up to 14. We can actually derive this from the Kw expression, but that's not really my goal right now. But pH plus pOH add up to 14. I want you to write this equation down as well, because it comes in really handy when we're trying to solve problems. So this opens up more flexibility in the kinds of problems we can do. So let's look at some of those. Problem number 4. Filtered tap water has a pH of 8.4 in this particular scenario. What's the hydroxide concentration? Okay, so here's the plan. This is actually a 2-step problem. I don't have an equation that goes from pH to hydroxide ion concentration. I do know that if I have the pH, I can calculate the pOH. And if I know the pOH, I can find the hydroxide ion concentration. Now, you might be thinking to yourself, wait a minute, there's something else I could do. You're right. There's another path through this problem. So there's a divergent path. It'll bring you to the same answer. And you're welcome to work that out and do it on your own. I'm only going to do one solution here. So I know that the pH plus the pOH add up to 14. So the pOH would be 14 minus the pH, which I was given. All right. And so I can find the pOH to be 5.6. Since I recorded the pH in the original problem with only 1 digit after the decimal, I'm going to report my pOH the same way. Okay, so I'm only going to have that 1 sig fig really in my pOH. Even though I have 2 digits written down, that 5's not considered to be a significant number, right? Okay. And once I know the pOH, I know 10 to the minus pOH will give me the hydroxide ion concentration because I have all these equations. All right, and so I can substitute in that pOH. Remember, I have to have that negative 5.6. 10 to the negative 5.6 will give me the hydroxide ion concentration, and I get an answer of 3 times 10 to the minus 6 molar. Again, I only get to have 1 sig fig in this final concentration for the hydroxide ion concentration. All right, so make sure you, understand the path of how I did the problems, but that you can also use your calculator to arrive at the correct answer. Let's go on and do another problem. Problem number 5. The pOH of arterial blood is 6.60. What's the hydronium ion concentration in arterial blood? Okay, so I'm given a pOH. I want H+. I don't have one equation that correlates these two, but I can do it in 2 steps. It's a 2-step problem, even though nothing tells you that. All right, but that's what it is. So if I know the pOH, from the pOH I can find the hydroxide ion concentration, just like we did in the previous problem. If I know the hydroxide ion concentration, I can use the Kw expression to find the hydronium ion concentration. Now, again, there is another path through this problem, but I'm only going to do one of them. You'll end up at the same place either way. So I know that the hydroxide ion concentration I can get from 10 to the negative pOH. So I can substitute in the pOH that I was given, and I get a concentration of 2.5 times 10 to the minus 7th molar. All right, so just the whole sig fig thing again. There are 2 digits after the decimal in my pOH. There are 2 sig figs in the pOH. And so I know my hydroxide ion concentration to 2 sig figs. And then I can go to my Kw expression. The hydronium ion concentration times the hydroxide ion concentration equals 1 times 10 to the minus 14th. I can rearrange that to solve for the hydronium ion concentration. I substitute in the hydroxide ion concentration that I just found, and I get 4.0 times 10 to the minus 8th molar. And again, I get to have 2 sig figs in that final concentration. Okay, there's one more problem I'd like to do. It's a little bit different from what we've been doing, but nothing you aren't ready for. All right, find the pH of a 3.67 times 10 to the minus 3rd molar solution of hydrofluoric acid, which is a weak acid with 3.2% dissociation. So this is a little bit different from what we've been doing. All right, I've got 3.2% dissociation. What I'm saying here is that only a very tiny number of the HF molecules here actually produce hydrogen ions in solution. So what we need to do is calculate the H plus concentration that's actually being released by the acids. Most of the molecules are staying as HF molecules and not making H plus ions at all. All right, because that's what weak acids do. So I can calculate the H plus concentration using that 3.2% dissociation. And once I have that, I can use the pH definition to calculate the pH. So let's go ahead and do that. So, all right, I need to take 3.2% of the original molarity I was given to find the H plus concentration in solution. All right, and I get 1.17 times 10 to the minus 4th molar. Now, if you're really paying attention, you're like, wait a minute, that 3.2% only has 2 sig figs. Yep, you're right. And my final answer will only get to have 2 sig figs. I'm going to round for sig figs at the end of the calculation. So now that I have an H plus concentration of 1.17 times 10 to the minus 4th molar, I can substitute that into my pH formula, negative log of H plus, put that in, substitute and evaluate, and I get a pH of 3.93. So again, remember, there were 2 sig figs in the percent dissociation, so I'm going to have 2 sig figs in my final answer, 2 digits after the decimal. Okay, I know the sig fig rules with pH calculations are not easy, but they are doable. So we're ready to wrap this up. I do want to point out it's really important to know these key equations. Write them down. The definition of pH, the negative log of hydronium ion concentration. Our math skills tell us that the hydronium ion concentration would then be 10 to the negative pH. Similarly for POH, it's the negative log of hydroxide ion concentration. We can find the hydroxide ion concentration from using 10 to the negative POH. And then we have those 2 other equations which are related to each other. The pH plus the POH add up to 14. And then the Kw expression, the hydronium ion concentration times the hydroxide ion concentration is 1 times 10 to the minus 14th. If you know these equations, you can do any pH calculation that you need to do. And this is a great place to stop. And I hope you have a great day and you go on and practice lots of chemistry calculations.